Welcome to this lecture. In this lecture, I am going to talk about Lorentz transformation. I will start with the Einstein's theory of relativity, or the square of the amplitude of the position vector, and try to derive Lorentz transformation. And these transformations are the orthogonal transformations in 4 dimensions. So for this, let us proceed as follows. So consider pseudo-Euclidean space your word point, your world point has the coordinates x0, x1, x2, x3, and these are defined as that x0 is simply ct, x1 as x, x2 as y, and x3 as z. Now the square of amplitude of position vector is defined as square of amplitude of position vector, defined as, here this is the position vector in one coordinate system, and there is another coordinate system, and if it is moving with the velocity v along the x-axis, then it is its position vector. So from here, this position vector, its square of the amplitude in the 4 vector space, it can be defined as, say it is x-axis or x prime axis, it is y-axis, y prime, and it is y, and it is z, it is z prime. So the square of the amplitude in this frame of reference, it can be defined as, this is x0 square, x1 square, x2 square plus x3 square, or you can simply write down it as x0 square minus x1 square minus x2 square minus x3 square. And this is an invariant quantity. So if it is invariant quantity, then it can be defined as x0 square minus x1 square minus x2 square minus x3 square. It must be equal to x prime naught square, x prime 1 square minus x prime 2 square minus x prime 3 square is the invariant quantity. Let me call it as equation number 1, and let me call it as equation number 2. Sorry, yeah. Now let us define a metric tensor. G mu nu and G mu nu, it can be written as G naught naught, G00, G11, G12, sorry, G01, G02, G02, G03, and G10, G11, G12, G13, G20, G21, G23, and G24, and not 1, 2, and 3. Sorry, it should be 2, 3, and it is 030, G0, G30, G31, G32, and G33, and it must be equal to 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, minus 1, 0, minus 1. This is with it how this metric tensor will be defined. So using this metric tensor, we can convert covariant vector into contravariant vector and vice versa. So let me call this as equation number 3, and using this metric tensor, we can define covariant vector as so x mu, it must be equal to g mu nu x nu, and summation over nu varies from 0 to 3. So if I elaborate this equation, then this equation can be elaborated as follows. That is, x mu is equal to g mu 0 x naught plus g mu 1 x1, g mu 2 x2, and g mu 3 x3. Here mu varies from 0 to 3. So if I keep on substituting these values of mu in this equation, then this may lead to x naught is equal to g00 x naught plus g01 x1 plus g02 x2, g03 x3, x1 is equal to g10 x naught, g11 x1, g12 x2 plus g13 x3, and x2 must be equal to g20 x0, g21 x1 plus g22 x2 plus g23 x3, and x3 must be equal to g30 x naught plus g31 x1 plus g32 x2 and g33 x3. Right. So this is where that how. So I can express these equations in the matrix form, and in the matrix form this equation will become that x mu must be equal to x naught, x1, x2, x3. It must be equal to g00, g01, g02, g03, g10, g11, g12, g13, g20, g21, g22, g23, g30, g31, g32, g33, and here it is x naught, x1, x2 and x3. And if I substitute the value here for metric tensor, then this equation may leads to then it can be written as x naught, x1, x2, x3 must be equal to 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. Now it is x naught, x1, x2, x3, and this must be equal to x naught minus x1 minus x2 minus x3, because when these gets multiplied, because it is of the order of 4 by 4 and it is of the order of 4 by 1, a number of rows in the number of columns in first must be equal to number of rows in second, and resultant will be 4:1, right? So this is a 4:1 order matrix. So this equation number 5 and this equation leads to following conclusion: that x naught must be equal to x naught, x1 must be equal to minus x1, and x2 is equal to minus x2, and x3 must be equal to minus x3. This is again the same equation, right? Now let us consider that x mu product of one covariant vector with the contravariant vector, contravariant and the covariant vector, and as I know that g mu nu x nu is basically the representation of x mu, and it is x mu, this will remain as it is, and this is basically written as in the form of a summation. This can be written in the form of a summation, so that means it is this one. So or I can express it as I can make use of summation here also. Mu varies from 0 to 3, and this part is basically, as we know from equation number 5, that it is x naught, x1 minus x2 minus x3. So it is a matrix of 4 by 1 order. So that means x mu, it must be equal to this if and only if this is a matrix of the form x naught, x1, x2 and x3, right? So that means, because this is possible, I simply applied the idea of matrix multiplication here. So that means this x mu, it must be equal to x naught, x1, x2, x3, x naught minus x1 minus x2 minus x3 So this leads to x mu, simply the product of these two. It is nothing but is equal to x naught square minus x1 square minus x2 square minus x3 square. Or if I use their values as I've taken in the beginning, so it will become ct square minus x square minus y square minus z square, or it can be written as ct square minus r square. So this equation, again, it can be written as, because if I expand this part, so this can be written as x naught plus x1 plus x2 plus x3. It must be equal to x naught square minus x1 square minus x2 square minus x3 square. So this is equation number 7. Now, as we know that if we are transforming from one coordinate system to another, then transformation matrix must be orthogonal. And orthogonal means transpose of a matrix product with itself. It must be identity matrix. And identity matrix, nothing but it looks like a delta function. It's in the form of a delta function, because here the diagonal entities must be unity. So that's what this represents, means delta function in the matrix form. Now to find Lorentz transformation, so to find mission, we have to make use of orthogonal transformation in Minkowski space. And the components of a 4-vector are transformed according to relation. Let me write down that expression. That means vector in primed coordinate system must be equal to transformation matrix multiplied by vector in unprimed coordinate system. Vector in unprimed coordinate system So mathematically, this can be written as x prime mu must be equal to alpha nu x nu, and summation over nu varies from 0 to 3. And initially the coordinates are intact, means the origins are at t is equal to 0, the origin of two frame of references will coincide, and the inverse transformation are also given by similar relationship. So inverse transformation can be written as that x mu must be equal to summation alpha nu mu bar x prime nu. So this is okay. So this is equation number 8, and let me call it as equation number 9. Here alpha nu is basically coefficient of transformation matrix, and alpha bar nu is basically represents the coefficients of inverse transformation matrix. Since equation number 2 suggests that equation 2 suggests that square of 4 position vector is invariant. So therefore, if that is invariant, so that leads to conclusion that mu is equal to 0 to 3. X mu, it must be equal to summation mu is equal to 0 to 3 x prime mu and x prime mu. This represents the invariance. And this is equivalent to, this equation is equivalent to equation 2. Now again reconsider this equation. If I reconsider this equation, then this can be written as mu is equal to 0 to 3 x mu, and it can be written as mu is equal to 0 to 3 g nu x nu. Here I have used equation number 4. Here I have used equation number 4. Similarly, if I used equation number 4 here, then this may lead to x prime mu and summation mu is equal to 0 to 3 0 mu nu x prime nu, right? So I can rewrite this part as it is summation over mu nu, and both are varying from 0 to 3. And here it can be written as g mu nu x mu x nu. It must be equal to summation mu nu varies from 0 to 3. That is g mu nu x prime nu and x prime mu. So let me now, here mu and nu are already used, and also we know that from equation number 8 that x prime mu is equal to nu is equal to 0 to 3 x alpha mu nu, and it is x nu. Since mu and nu are already used, so what we will do, we will use here, say in place of this, what I will do, because it is shifting from mu to nu. So that means what I will do, I will express these in the similar fashion but with this different indices. So that means x prime mu, it can be written as summation over alpha rho mu and x rho, and this summation is varying from 0 to 3. And similarly I can use x prime nu at summation sigma varies from 0 to 3 alpha sigma nu and x sigma. I can use these two here, and if I use these values in this equation, then what this will become, this equation can be written as, this is summation mu nu varies from 0 to 3, it is g mu nu x mu x nu. It must be equal to summation mu nu 0 to 3 and g mu nu and summation rho varies from 0 to 3 alpha rho mu x rho and summation sigma varies from 0 to 3 x nu sigma, alpha nu sigma, and it is x sigma. Now these sigma and rho, these are the dummy variable. So what we can do, we can replace mu by rho and nu by sigma. Means if we will exchange these, so if I exchange, then what will happen, this equation will become so here I will exchange, then this will become x mu x nu, right? And another thing, it is g rho sigma and alpha. Here I am just exchanging. So if I exchange, then mu will be here and this will be here, and also mu will be here and this will be here. In this equation I just exchange these, and here now it is the 0 to 3, and here it is varying from 0 to 3. So that means G mu nu x mu mu nu varies from 0 to 3. So this is possible if and only if this part is equal to G mu nu, right? So this is possible. If this part is equal to this one, which means that G mu nu, it must be equal to rho sigma varies from 0 to 3 and G rho sigma alpha rho nu and alpha sigma nu, right? So this is equation number 12, and this is a very important equation which we are getting. So that's what I am getting here. Now from equation 3 it is clear that G it is equal to 0, and in other words I can say that this is equal to 0 and not equal to 0 for rho is not equal to 0 and for rho is equal to 0, and the equation this 3 will suggest that this G mu nu it must be equal to let me express it, write down it with a different color. Yeah, so it is G mu nu or G sigma, it is 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1, right? So this thing will suggest that if then for diagonal entity it is non-zero and rest of it is 0. So that means for diagonal entities this it is equal to this one. If I will use this in this equation 12, then this may leads to this equation will become G mu nu must be equal to summation rho varies from 0 to 3 and G rho x rho mu and x rho nu, and this is equation number say 12 and sorry 13, and let me call it as equation number 40. Now and if I express this part here and this side, if I use this, and for nu is equal to 0, if both are 0, then this from this equation how things can be written as it is x rho 0, sorry it's not x but sorry it is alpha Okay, it is alpha, right? So it's alpha, and it is alpha rho because mu and nu both are 0, and rho varies from 0 to 3, and it is G00. So this leads to, because if I substitute this value here, or if I open the summation, then it is G00 alpha 00 alpha 00 plus G11 alpha Z10 alpha 10 plus G22 alpha 20 alpha 20 plus G33 alpha 30 alpha 30, and must be equal to 0. And if I use this part here, say if I use this part here, that means the value of this will be 1, its value will be minus 1, its value will be minus 1 from this part, and its value is also minus 1, and its value will be 1. So this may leads to the equation that alpha 00 square minus alpha 10 square plus alpha 20 square plus alpha 30 square, it must be, sorry, minus will be there, alpha 20 square plus alpha, minus alpha 30 square, and it is equal to 1, right? So that's what we are getting. And similarly, for mu is equal to 1 and nu is equal to 2, we can write down rho is equal to 0 to 3, g rho alpha rho 1 and alpha rho 2 and G12. So from here I can write down it as G00 alpha 01 alpha 02 plus G11 alpha 11 alpha 12 plus G22 alpha, it is alpha 21 alpha 22 plus G33 alpha 31 and alpha 32. It must be equal to G12, and its value will be 0. Its value is minus 1. Its value is minus 1. Its value is minus 1, and its value will be 1. Right? So if I substitute these values, this equation alpha 01 alpha 02 minus alpha 11 alpha 12 minus alpha 21 alpha 22 minus alpha 31 and alpha 32, and it must be equal to 0. So this is equation number 14. So we will get two results. One result is this one, and another result is this one. Now let us find out the relationship between coefficients of direct and inverse transformation. So for that, consider equation 9, and the equation 9 is this one: alpha mu nu bar and x prime nu, and nu varies from 0 to 3. So if keep this mind, then we will simply change the dummy variable, means nu is replaced by rho. So if nu is replaced by rho, so that means using this equation number 9, we can write down at x mu is equal to rho varies from 0 to 3, alpha rho mu x prime rho, right? It's a bar because it is inverse transformation matrix. But as we know that x prime mu must be equal to nu varies from 0 to 3, alpha mu nu x nu. This is equation number 8. So if I use this equation here, then this can be written as rho varies from 0 to 3, alpha bar mu rho, and using this part will become summation nu varies from 0 to 3 and alpha rho nu and x nu. So that means this equation x mu must be equal to summation nu varies from 0 to 3 x nu and summation rho varies from 0 to 3 alpha bar mu rho and alpha rho nu. So this is the equation number 17. And this is possible if and only if this looks like a delta function. That means this is possible if and only if this summation rho varies from 0 to 3, alpha mu rho bar and alpha rho nu, it is delta mu nu, and delta mu nu, it is equal to 0 or 1, where mu is not equal to 0 and mu is equal to nu, right? So let me open it. So that means this equation can be written as this: alpha bar mu 0 alpha 0 nu plus alpha bar alpha 1 nu plus alpha mu 2 and alpha 2 nu plus alpha bar mu 3 and alpha 2 nu, it must be equal to delta mu nu. Now for mu nu both are equal to 0, in that case this equation will become that alpha bar 0 0 alpha 0 0 alpha bar 0 1 1 0 plus alpha bar 0 2 and alpha 2 0 and alpha bar 0 3 and alpha 3 0 must be equal to 1. And this is equation number 18. Now if I compare equation number 15, with it, if I compare equation number 15, and what is the equation number 15? Let me recall that equation number 15. Equation number 15 is alpha 0 0 whole square minus alpha 1 0 whole square minus alpha 2 0 whole square and minus alpha 3 0 whole square. It must be equal to 1. So these two equations looks identical if and only if this part is basically, if this is equal to alpha 0 0 and this is equal to alpha 1 0 with negative sign, if it is alpha 2 0 with negative sign, and this is equal to alpha 3 0 with negative sign. I'm just talking about this part, right? This is possible. So that means from here I am writing it as that alpha it must be equal to alpha 0 0 or alpha 0 1 bar must be equal to alpha 1 0 with negative sign, and alpha 0 2 bar must be equal to alpha 2 0 with negative sign, and alpha bar 0 3 must be equal to alpha 3 0 with negative sign. Or in general I can write down it as alpha 0 0 and alpha 0 I, it must be equal to alpha 0 I. Here I varies from 1, 2 and 3. And similarly we can prove that. Similarly we can write down alpha I 0 bar must be equal to multi I 0 and alpha I k bar must be equal to alpha k I, where I and k varies from 1, 2 and 3, right? So that's what I am getting here. So that's what we are getting here. So let me sum up these results now. So if I sum up these results, that means alpha 0 0 bar must be equal to alpha 0 0, alpha I 0 bar must be equal to alpha I 0 with negative sign, and alpha I 0 bar must be equal to alpha 0 I with negative sign, and alpha ki is equal to alpha ik, and where I and k both varies from 0, 1, 2 and 3. So let me call it as equation number 3. Now, since we know that x2 is equal to y and x3 is equal to z. These are invariant, or these remains unchanged as frame of reference is moving along x-axis only. So that means this y and z remains the same. So if they remains the same, then the matrix alpha mu nu, it can be written as alpha 0 0, alpha 1 0, alpha 0 2, alpha 0 3, alpha 1 0, alpha 1 1, alpha 1 2, alpha 1 3, alpha 2 0, alpha 2 1, alpha 2 2, and alpha 2 3, and alpha 3 0, alpha 3 1, alpha 3 2, alpha 3 3, and it's simply equal to alpha 0 0, alpha 0 1. Rest of the terms will vanish. Alpha 1 0, alpha 1 1, this is 0, this is 0, this is 0, 0 1 0, 0 0 1 0 and 1. Also consider in the similar way, let us consider alpha mu rho and alpha rho nu. So it is alpha 0 0, alpha 0 1, it is 0, it is 0. Here it is alpha 1 0, alpha 1 1, it is 0, it is 0, 0 0 1 0, 0 0 0 1, and here it must be equal to alpha 0 0, alpha 0 1 0 0, alpha 1 0, alpha 1 1 0 0, 0 0 1 0, 0 0 0 1, and it must be equal to delta function. If I open it, then it means that alpha 0 0 bar 0 0 plus alpha 0 1 bar alpha 1 0, and here second term will be this one. It's simply the product of two matrices. Here it is 0, here it is 0, and it is alpha 1 0, alpha 0 0, alpha 1 1, and alpha 1 0. Now it is alpha 1 0, alpha 0 1, alpha 1 1 bar and alpha 1 1, and it is 0, it is 0, it is 0, it is 0, it is 1, it is 0, it is 0, it is 0, it is 0, and it's 1, and it must be equal to 1 0 0 0, 0 1 0 0, 0 0 1 0, and 0 0 0 1, and say it is equation number 21. So if I use equation number 19 here, using equation number 19 for this part, then this may lead to alpha 0 0 whole square minus alpha 1 0 whole square, it is equal to 1. Say 20, equation number 20 it is 20a, and let me call it as equation number 21. So similar relationship hold for the coefficients of the inverse matrix. So similarly, for inverse transformation 0 0 its square minus alpha 1 0, its square must be equal to unity, and let me call it as equation number 22. So if I use equation number 19 here, using equation 19 here, then this will become 0 0 whole square minus alpha 1 0 whole square is equal to 1, and this is equation number 23. Right? Now again consider equation 14. If I consider equation 14, for mu is equal to 0 and nu is equal to 1, then equation number 14 can be written as rho is equal to 0 to 3, 0 rho, alpha 0 rho, and alpha rho 1, and it is equal to z01. And let me open it, g00, alpha 00, alpha 01 plus g11, alpha 10 and alpha 11 plus g22, alpha 20 and alpha 21 plus g33, alpha 30 and alpha 31, g01. Its value will be 0 and its value will be minus 1. Its value is minus 1, its value is minus 1, and its value is for this one. And as we know that this y and z remain unchanged, so these two terms can be neglected. If I neglect those, then this equation will become alpha 0 0 and alpha 0 1 minus alpha 1 0 and alpha 1 1 is equal to 0, and let me call it as equation number 24. This is neglected because x and y remains the same. X and y remains the same. Now let us compare equation number 21 and 23. And 23. So both are identical to same term. So keeping that in mind, that alpha 1 0 its square must be equal to alpha 0 1 whole square. So this leads to the conclusion that alpha 1 0 must be equal to plus minus alpha 0 1, and this is equation number 25. Again consider equation 24. So if I consider equation 24, then alpha 0 0, alpha 0 1 must be minus alpha 1 0 and alpha 1 1 is equal to 0. So if I use here that alpha 1 0 is equal to alpha 0 1, then using this alpha 0 0, alpha 0 1 must be equal to alpha 0 1 and alpha 1 1. This will cancel out with it, right? So this leads to the fact that alpha 0 0 alpha 1 1. That means if I sum up this result, that means alpha 0 0 must be equal to alpha 1 1 if alpha 1 0 is equal to alpha 0 1. Similarly, again, if I consider that alpha 0 0 alpha 1 0 is equal to alpha 0 1 and alpha 1 1, and if I use the fact that alpha 0 1 is equal to minus alpha 1 0, if I use this here, then alpha 0 0 alpha 1 0 must be equal to minus alpha 0 1, and here it is alpha 1 1, which means that alpha 0 0 is equal to alpha 1 1 with negative sign. So to sum up this result, I can write down it as alpha 0 0 is equal to alpha 1 1 with negative sign. If alpha 1 0 0 1 is equal to minus alpha 1 0, right? So this is another thing which we are getting. Now I will consider only question number 26. So using equation 26, that is alpha 0 0 is equal to alpha 1 1 and alpha 1 0 is equal to, right? So using this alpha mu, it can be written as alpha 0 0 alpha 0 1. It is 0, it is 0, it is alpha 0 1, and it is alpha 0, means they looks identical, keeping this fact in mind. And it is 0 0 1 0 0 0 0 1. Or I can do one thing. Its actual value will be this one, 0 1, and here it is 0 1, and it is 1 0. Its actual value will be 1 0, and it is 1 1. So if I use this in this case, so then it will become alpha 0 0 alpha 0 1 and alpha 0 1 and alpha 0 0 0 0 0 0 0 1 0 0 0 0 1, right? Now consider that x mu prime must be equal to alpha mu nu x nu. If I use this, then using this I can express it as x prime 0, x prime 1, x prime 2, x prime 3. It must be equal to alpha 0 0 alpha 0 1 0 0 alpha 0 1 and alpha 0 0. It is 0, it is 0, and it is x0, x1, x2 and x3. So this leads to the equation that if I open this, that means x0 prime is equal to alpha 0 0 x0, alpha 0 1 x1 and x prime 1 is equal to alpha 0 1 alpha 0 x0 plus alpha 0 0 x1 and x prime 2 is equal to x2 and x prime 3 is equal to x3. and let me call it as equation number 29a. And if I substitute their values, then this may leads to the Ct prime is equal to alpha 0 0 Ct plus alpha 0 1 x, and x prime is equal to alpha 0 1 Ct plus alpha 0 0 x. This is equation number 30 and this is equation number 31. These two equations can be written in this form. Now let us consider the case when O prime or x prime is equal to 0, when origins will coincide. So that means x prime is equal to 0 and x is equal to vt. If I consider this case, then equation number 31 leads to this is equal to 0 is equal to alpha 0 1 ct plus alpha 0 0 vt. Right? I have used this fact here. So this means that alpha 0 1 comes out to be minus alpha 0 0 v over c, and this is equation number 32, this is 33, and this is equation number 34. So now consider alpha 0 0 whole square minus alpha 0 1 whole square, it is equal to 1, and it is alpha 0 0 whole square minus, I substitute its value here. So if I substitute its value, it is minus alpha 0 0 v over c whole square, and it must be equal to 1. So I can take it outside, so it is 1 minus v square over c square, it is equal to 1. So that means from here alpha 0 0 can be written as 1 minus b square over c square under the root. And using equation 34, so using 34, alpha 0 1 comes out to be minus v over c over 1 minus v square over c square under the root. So these are the two values which we are getting. And this leads to transformation matrix for the Lorentz, this leads to Lorentz transformation matrix as, so Lorentz transformation matrix can be written as alpha mu nu as 1 over 1 minus b square over c square under the root minus b by c 1 minus b square by c square under the root. It is 0, it is 0. It's minus b by c over 1 minus b square by c square under the root. It is 1 over 1 minus b square over c square under the root. It is 0, it is 0. It is 0 0 1 0. It is 0 0 0 1. And let us call v over c as beta. So if I use this, then this equation can also be written as 1 over 1 minus beta square under the root minus beta over 1 minus beta square under the root, and minus beta over 1 minus beta square under the root, and 1 over 1 minus beta square under the root. It is 0, it is 0, it is 0, it is 0, 0, 0, 1, 0, 0, 0, 0, 1. So I can express it in this form, and let me call it as equation number 37. And therefore equation number 29a can be written as, so using these values in equation number 29a, I am getting x prime naught is equal to 1 over 1 minus beta square under the root x naught plus minus beta over 1 minus beta square under the root x1, and this can be written in the form x, this is equal to x prime naught is equal to x naught minus beta x1 over 1 minus beta square under the root, and x prime 1 is equal to minus beta over 1 minus beta square under the root x naught plus 1 over 1 minus beta square under the root x1. It can be written as x prime 1, it is equal to beta x naught plus x1 over 1 minus beta square under the root, and x prime 2 is equal to x2, and x prime 3 is equal to x3. And say this is equation number 38. And if I use x prime naught is equal to ct prime, x naught is equal to ct, x1 prime is equal to x, and x prime 2 is equal to y prime, and x prime 3 is equal to z prime, and x1 as x, x2 as y, and x3 as z, then we will get t prime is equal to t minus v x over c square over 1 minus beta square under the root, and x prime is equal to x minus bt 1 minus beta square under the root, and y prime is equal to y, and z prime is equal to z. So these are basically Lorentz transformation. And we have derived these from the special theory of relativity. And in the similar fashion, we can find out the inverse Lorentz transformation by changing beta to minus beta and unprime to prime. So that means this is x naught is equal to x naught prime plus beta x prime 1 over 1 minus beta square. These are the inverse Lorentz transformation. x1 is equal to beta x naught plus x1 over 1 minus beta square under the root, x2 is equal to x prime 2, and y x3 is equal to x prime 3, or these may be written as that t is equal to t prime plus bx prime over c square over 1 minus beta square under the root. This is x is equal to x prime plus vt prime over 1 minus beta square under the root, and this y is equal to y prime and z is equal to z prime. So this is all about Lorentz transformation. And inverse Lorentz transformation, we have used the concept of orthogonality, and we started with the Einstein's equations of special theory of relativity, and we have derived it. So thanks for watching this video.